Situationally aware dynamics learning via online hidden state representation learning. We evaluate our situationally aware dynamics models against physics-based and learning-based baselines. We begin by testing the physics-based and learning-based methods in a hard task. In this scenario, the robot must climb a high-sloped mountain with many holes that hinder its motion, which forces the robot to replan to get unstuck. Here, the PEY method fails to steer the robot to the goal. You can also see the physics-based Dubin's model get stuck on a bump. Since this dynamics model is unable to incorporate new terrain information according to what the robot is experiencing, the planner keeps selecting an ineffective action. The PERPY model incorporating all orientation information also fails as it is unable to overcome a muddy region. Our model can clear the mountain. Similarly to the Dubin's model, our model got stuck but it was able to replan as a situation change prompted a change in the dynamics model, resulting in the planner selecting new actions based on the new dynamics constraints. We now verify that our situationally aware dynamics model can overcome a slippery, muddy area. Note that this is the same area where other models failed in the previous task. As you can see, our method is able to clear the muddy region in all 5 trials. We proceed to compare the best performing baseline with our model. Here, we ask the robot to descend a very steep mountain with many irregularities and come back. As it is possible to see the baseline failed to adapt and puts the robot in a dangerous irrecoverable state. On the other hand, our method generates behaviors to go down safely and overcome the terrain irregularities which represent a significant challenge given its low profile. We repeatedly see how the hidden state representations inform the dynamics, which leads the downstream planner to generate safe behaviors. We also see interesting behaviors emerge during unstructured terrain navigation in the real world. Upon a situation change, the robot revises its plan via the informed dynamics model and tries to generate behaviors to successfully reach the top. While going downhill, the robot is more cautious and moves slowly. Note that given that this terrain is smoother and less steep than the one in previous tasks, the robot's path is no longer curvy and instead approaches its goal directly. Once on safer, flatter terrain, the robot autonomously decides to move faster and with less caution. Now we test on a very hard task. Here the robot has to climb a muddy high-slope mountain. Again, our method successfully reaches the objective in all 5 trials. Finally, we present our model successfully moving through multiple other environments and tasks. Thank you.